YouTube channel. I am very excited that we have Dr. Franklin Dollar from the University of California, Irvine, who will be speaking to us today. Dr. Dollar is a native of California. He grew up, well, albeit, I believe, Northern California, but he's a California native and is a member of the Dry Creek Band of Pomo Indians. He got his BS from Berkeley and then his master's and PhD at the University of Michigan. And he specializes in working on plasma physics. He has a very long bio with lots of accomplishments. So rather than me just list it, I am going to turn it over to him because I know he's going to tell us a lot about his story and how he got where he is today.
Thank you, Dr. Kalori. And thank you everyone who's turned in to go watch me speak today. It's a little odd of a venue to try to make this work, but I'm glad we are trying to make it work. And so as part of this Diversity in Science seminar series, I'm going to be giving my talk called Searching for the Brightest Light. And what it's going to be is a talk that's kind of my own journey from high school to where I'm at now, and then going ahead and saying how I've been able to establish myself as a research faculty at the University of California, Irvine, what that research program looks like, and just a little bit of a flavor of some of the research that we're doing. And as a spoiler alert, a lot of the physics I do is related to lasers and light. And so searching for the brightest light is going to be a bit more apt as the farther along we get through the talk. So I'll go ahead and begin, and hopefully things are okay tech-wise. If there are any kind of hiccups or anything, feel free to go ahead and let me know so that I can go back a step. So as Sarah mentioned, I'm a California native in the sense that I'm from the Dry Creek Band of Pomo Indians. California has a lot of tribes and they're scattered all throughout California. The area where I'm from is in Northern California in Sonoma County, and this general region up here is a collection of tribes called the Pomo Tribes. And whereas, maybe if you look in a map, there'll just be one word describing this area. This is kind of showing the different reservation lands that exist in Northern California. You can see there's a lot listed there. And one of the reasons for this is that calling this whole region Pomo is kind of like calling all Europeans in the sense that there are some similarities between, say, being French and English, and there's some similarities in the language, but certainly they may not get along real well once they're next to each other. So the band that I'm in is actually a Southern Pomo. There's 7 different regions of Pomo, and the Dry Creek Band of Pomo Indian is my particular band, which is located, right here in Sonoma County. Now, I do want to point out that this map right here is just showing current tribal lands, and for a variety of reasons, there's not a lot of them left. Many tribes in California no longer have any lands, and in particular, the lands that University of California, Irvine occupies were part of the Accochement and Tongva tribes, which have no current lands entitled to them through vested by the state or the federal government, yet all of this land was Accochement and Tongva not too long ago. So I just want to give that acknowledgement. And so here is a Google Earth photo from approximately 20 years ago when I lived on the reservation. And it was a very different time than it is today. Today, there are things like a casino and a resort and restaurants and things of that nature. They're developing some vineyards in the area. But when I lived there, which was these types of enterprises were developed, it was just housing, and not houses, but typically mobile housing. So the housing that I lived in was a type of trailer that was actually not for sale by California, because California has codes that prevent it from being used for accommodations. However, those laws don't apply on reservation land, and so it was a way to have very affordable housing. Where I lived, we had some septic, but there was no running water and electricity until last couple years that I lived there in high school. And so that's very interesting because adjacent to the Dry Creek Rancheria are some of the most nicest vineyards in California. So it's a billion-dollar industry, lots of wealth concentrated in this area right there. However, at the time, it was one of the most impoverished places in the county. And so leaving there, so before I get to that, I attended the local high school, which was a public high school. It was the Geyserville Educational Park, which was a combined middle school and high school. Our mascot was the Broncos, with its unique spelling there, since we were having a conversation on mascots earlier. And for a comparison, here's the 2015 graduating class. And there's not a lot of people in that photo. We actually had the largest graduating class in 2002 of 38 students. And that was kind of a high point for the school there. But it was a unique experience because we were at a high school where it was a mixture of those of us from the reservation and those of us whose parents may have been involved with the vineyard industry, whether that may be through managing vineyards or through working in the field. So it was kind of a diverse mixing pot of different cultures and people, even though there weren't that many of us at this high school. From there, as mentioned in my brief bio, I went to University of California, Berkeley, then onwards to University of Michigan. I did a postdoc at GILA, which is an institute at CU Boulder, and I ended up as faculty here at UCI. That's the abridged version of my journey. I'm going to talk a little bit more about the early parts, in particular because if I go back and you see, this is my entire class for high school. Whereas when I go to the University of California, Berkeley, classes look a little bit differently. And in fact, I can be in a lecture hall that has more people in it than lived on the reservation lands where I grew up on. And in fact, you know, this is a picture of my graduation where there's thousands and thousands of people there, many more than even lived in the town of Geyserville. So it was a little bit of a culture shock to go to some place where everything's pretty remote and out of the way, and a lot of these interactions and social networks are much smaller than they would be going to a place like University of California, where there's more people in, say, my intro physics class than there would be in the entire school system of Geyserville. And so that's a bit of a culture shock. And coming from those types of environments to a very large public institution can be daunting, as many in the audience may very well know and understand. And I had a very, very hard time when I first went to Berkeley. I really had no idea how to study. I really had no idea what to do. My first FAFSA had a family income less than $20,000. So I was able to max out things like the Cal Grant and the Pell Grant, but there were still significant burdens left over from things like housing. In 2002, I had the cheapest dorm option at Berkeley, which was approximately $1,000 a month. And all of that combined together made it very difficult to get by. So I had to work a lot. And so all of these factors combined made my first year there very, very difficult. I ended up failing and having to retake my first physics class, which, you know, is interesting because now I'm a physics professor and I teach said class. But it certainly didn't make me feel like I would be able to go back and complete the degree, let alone have a career in this field. And these were voices that had come across through different things in terms of the advising, or, you know, maybe in this case, it might be better to call it lack of advising. A lot of times the advising might just be, oh, it looks like you're doing pretty bad, you should probably leave now. And I don't think that's effective advising, yet this was the advising that I had at the time. When I initially signed up for far too many classes and I was trying to drop a class, my student affairs advisor asked me if I even cared about graduating on time and if, you know, it was even worth staying in the school, let alone the major. I was looking to take a upper division mechanics class, and the faculty advisor I had, they actually didn't say maybe you shouldn't be in this major. They used the wording, maybe you shouldn't take hard classes like this. And I pointed out that these classes were required for my major, and they said, I know. You know, and trying to recover from a very poor first year meant that your GPA is marred and scarred, and you're marked for the rest of your time there. And so that's the thing that people associate with you if they just glance at your application. And so you don't get a lot of confidence from these types of conversations. Thankfully, though, I was able to find a large network of other programs that was able to help me understand my own worth and my own path forward so that I could find my own success. The native groups at Berkeley were particularly useful. When I first got there, I didn't even know where they were, how to find them. And so thankfully, by the end of my first year there, they found me. One of the staff who worked at admissions reached out to me and was wondering if I'd like to come in for some meetings. And so that's when I first started working with the Native American Recruitment and Retention Center at Berkeley and really started developing that social network. There was also the multicultural engineering program, which I believe has been merged into some other programs in the engineering program. But that was another very, very core component of me building out a social network and understanding what kind of resources were available and how to work. And along the way, I was working, trying to get money to pay for everything that was going on there. And I just continued doing what I used to know to do for money. And that was working at the, so at the time it was a Long's drugstore. Now it's a CVS, but working at the local CVS to make ends meet. It's what I had done in high school, and it's what I continue to do because I didn't know of better ways of making money. And through the UC Leeds program, which unfortunately I forgot to place their icon on here too, I was introduced to the concept of being able to do research as an avenue towards not only being able to pay for things, but being able to pay for things and have professional development along the way. And so I got paid much more money to go ahead and do research. I could commit less time to it, and it could be very flexible with my schedule so that I could actually spend time meeting with people, working on homeworks together, becoming better academically, while also gaining all of this experience on the side. And I ended up getting involved with a lot of research. At the time, I thought that this was the best scam I'd ever heard of, where I can go and spend 8 weeks over the summer and get paid thousands of dollars with housing and other opportunities included. I just couldn't imagine such a thing was possible. And then on top of this, it also turned out that they'd pay for me to go to conferences to present my work. And being able to just be on a plane was just something that sounded amazing to me. The thought of staying in a Marriott was just this amazing concept. And, it was kind of just this, it seemed so good, that too good to be true at the time. And so I got involved with a lot of different research programs. I got involved with, and you'll note that a lot of them have the NSF logo by it. So for instance, I did research internships with Engineering Research Center, the EUV ERC, a Materials Research Science and Engineering Center. I also did programming with the Louis Stokes Alliance for Minority Participation. And through a combination of different ones of these programs, I learned different skill sets and I gained confidence, and I learned that I could actually do science. And even though I had lots of advisors that weren't giving me great advice for how I can actually succeed, they were giving me advice how to leave, which I don't think is maybe should be the purview of that person. But these programs were able to come in and actually train me in skill sets that would serve me for the long haul. Also, I'd be remiss if I didn't mention the American Indian Science and Engineering Society. So I started attending their conferences in 2003 and very quickly ended up in leadership positions and being able to, go from being a shy kid from the reservation that didn't know how to approach everyone to being the talkative, rampant person in front of you right now. And so I've been going to the conferences for a very long time, and that network has always been there for me, and I'm very appreciative of the network that exists there. Very briefly, I'll go through some of the research experiences I had and some of the things I took away from it. My first research experience was up at Lawrence Berkeley National Labs. And in particular, I was able to go ahead and work at the Advanced Light Source. And so this is a big giant machine that's a particle accelerator, but it doesn't really care about making the particles. If you have an energetic particle and you accelerate it in any way, it radiates light. And if you accelerate it violently enough, it'll radiate very high energy, right? Light or X-rays. And that's what happens in this machine here. So we generate very energetic beams of electrons and we move them in a circle. And as we know, changing the direction is an acceleration. So that causes there to be a radiation event, and we can use this light that's produced for a variety of scientific reasons. In particular, what I was looking at in this research experience was understanding some of the properties that different materials had. It turns out that light in the extreme ultraviolet, which is this range between around 100 nanometers and 1 nanometer, it's very difficult to make light there, and practically everything absorbs light in that region. So if you do make that light, it's almost immediately absorbed by something. So that's problematic because really you just need a vacuum to make it work. The good thing about it though is because everything absorbs that light, it absorbs it a little bit differently. So it can give you a lot of information on, say, what elements you might have there. So if you look at some elements and see how they absorb at different energies, you can identify which elements could be part of something. And so we would call that element specificity. Some of the things that I looked at were, because it's so hard to make light here, we had a very, very nice spectrometer and monochrometer, so we can go ahead and look at exactly how materials respond to this. So I was able to do some very high resolution studies of materials and look at things like the absorption with details that just hadn't been looked at before. And so this involves making very nice high purity niobium targets that were just a few hundred nanometers thick, and then changing them in thickness and trying to understand the relationship between how light's absorbed in them and across this region and the material properties itself. We then use this information to design different types of mirrors that are highly reflective in this region. Whereas it's fairly easy to make a mirror that reflects light in the optical wavelengths, it's much more difficult to do this in this extreme ultraviolet wavelengths. And so you really need to know the optical properties really well in order to make a high quality mirror. And that ended up being one of the first publications that I was part of. And the amazing part of it was that I didn't even understand that what I was doing was physics. I got to go in and work with these big machines and glove up and carefully tune them and perform all these measurements. And I just thought that was a job that I was doing. I didn't understand that science was what I was doing because it didn't really look like anything I was covering in my classes. On the flip side, I learned a lot more about the Beer-Lambert law by seeing how absorption played out in real life than I ever did in my classes. In fact, it wasn't until later that I made the connection that what I was seeing in the real world was something that was in a textbook somewhere. So by doing enough of this work in the lab, I was able to start understanding what it was we were trying to understand in our coursework and majors. Taking this experience on making these very high quality extreme ultraviolet mirrors, I was then able to do a research experience with Lawrence Livermore Labs, in which we were able to develop the optics for the Solar Dynamics Observatory. So shown right here is our photo of our cartoon of the Solar Dynamics Observatory. And there's these 4 canisters up here that are color coded that each held some spherical optics that were coated with these high quality mirrors that I had helped work on. So we worked with them to actually build the mirrors that would be put inside the satellite, which now currently is orbiting the sun and taking measurements of that. And so this has been up there for, I think, almost a decade now. We're getting lots of great information. And one of the novel things about these mirrors is that we can coat different parts of the mirror to reflect the different wavelengths in the extreme ultraviolet. Because of that, we can see how, say, iron is being emitted from the sun, and different temperatures of iron will emit different wavelengths. So we're kind of getting a color mapping of the sun by seeing it with all these different wavelength channels. And this is all in the extreme ultraviolet. And it works because there's not a lot of things that can absorb between the sun and our satellite. So we have a nice clear line of sight to be able to go ahead and image the sun. And so that was the instrument I was able to work on. And it was pretty exciting because I still thought that, at this point of the game, I thought I was still working on some projects that wouldn't lead to anything. And here was something where I could actually hold this $200,000 optic that we then put in a box and ship to JPL to load up into the satellite. So it was actually, the awe that I felt. I don't think I have any words to describe otherwise. Finally, for my third research experience, I did this one at Harvard University. And what was really nice about this was that I had a lot of autonomy in the research that I was able to do. So this is a picture right here showing the research area that I had set up to go do work in. And the research project I had here was a little bit different. My research project was to go ahead and try to make really tiny droplets. If you could make droplets that were, say, on the order of a few hundred nanometers, you can maybe put in a single molecule and then do chemistry in the single molecule droplet. And the idea of trying to make this work was using electric fields to try to shape the droplets to make that work. Well, I immediately turned up the electric field too high and it exploded the whole thing. And that was the last day of that experiment, but also the first day of another, because I left on all of my cameras. And what we saw was a very odd phenomenon. So normally if I have two water droplets and they touch, they'll go ahead and coalesce into a larger water droplet. But what I was observing in this exploded setup was that these water droplets would touch each other, but then bounce away from each other. And that seemed very odd. And I showed it to my advisors and they also agreed it was very odd. And it became the new research project for the summer. What we end up figuring out through a variety of different experiments on this is that those water droplets can contain a lot of charge. And the local way of how these two droplets can basically kiss each other can exchange all that charge and then pull back with the same electric field force. Now that the charge is exchanged, there's nothing pulling them back together. They pull back, and now they're bouncing back and forth, exchanging all of this charge, similar to a fire brigade holding buckets of water. So each droplet takes its charge and it can pass it to the next droplet, and then that droplet can pass it to the next droplet across one electrode to the other one. And this was very interesting scientifically, and we're able to go ahead and get it published in Nature, which was pretty successful given that it was still this random undergraduate research project. And so that was a fantastic summer that I had. And it, one of the reasons I'm talking about these research experiences so much is you gain a lot out of them. You learn how science works, and a lot of times it's non-linear in the sense that you don't really know what you're going to see. The best science kind of happens from these kind of happy accidents. Another way that I've heard it put is when you're in the lab, the publishable data comes from the last day of the experiment. And it doesn't mean the rest of the time was wasted. It means the rest of the time was spent searching for that thing that we didn't really understand. Nature is very, very good at being nature, and we as humans, we do our best to understand it, but a lot of times we can get things wrong. And so when we do the experiment, we're in a way letting nature guide us towards these results and help us see these types of things, but we can only do it if we look. The other thing that was great about this is that working with lots of different people gives me a lot of different letters of recommendation, so that I'm not just a one-dimensional GPA number. I also have all of these other people who can write letters about the work I'm able to do and the commitment to it, how I understand this material in practice. And those are things that are arguably more than just having one number attached to you. I do want to make one other point, since it's around the time that students are applying to the Graduate Research Fellowship. I also applied to the Graduate Research Fellowship, and As you may know, you're allowed to apply as many times as you want as an undergrad, but you're only allowed to apply one time as a graduate student. When I was an undergrad, I applied and I did not get the NSF. However, as a graduate student, I applied and I did get the award. And what's very interesting is there was about a year in between both applications. And after I had won it, I discovered you can look up the reviews. And the reviews were basically, they couldn't have been more opposite. The first set of reviews were all very low scores. It was, you know, very, I'm glad I didn't read them, because if I had read them, I probably wouldn't have applied the second time. But then when I read the second set of scores, they were, you know, they were all excellence, and they talked about being an ambassador of the field and all these other things. And at the time, it was kind of confusing because, you know, I wasn't that much older. I didn't really know anything more than I did before. I was basically the same person. And the key thing for that is that there were two students, in the sense that when I applied as an undergrad, I did the thing where I wrote up a really good first draft and then sent it out that week. And when I was in grad school, I wrote a draft, and then I rewrote a draft, and then I rewrote a draft, and I went through about 12 different drafts before I finally had something that I felt was good to submit. And even then, I was still refining it right up before the deadline. And I think there's this feeling that we get when we do things like write, where we don't want to hand something bad out. But what I like to say in this is that, you know, even J.K. Rowling and Stephen King and authors like this have editors. The first draft is always going to be the first draft, and the best first draft is still a first draft. And that's okay. Once we accept that and move on to the second draft, the key thing that happens is we get feedback, and then we can work on the iteration. And the more we take that feedback and the more we do that iteration, the better our writing becomes. Even if you're a great writer, you still need to do those steps. And that was really the only difference between these two applications. And it was very clear, and now that I've reviewed such applications, it's very clear to me when someone's turning in a first draft and when someone's turning in something that they clearly iterated on. So in graduate school, I really liked the idea of light and matter. And so I wanted my graduate career to be out of it. And so I immediately started working in a research group on organic semiconductors. And for a variety of reasons, it ended up not being quite a good fit for me. So I ended up switching out of what I thought would have been my graduate career into a completely different field that was on laser matter interactions, really high intense lasers. And so here's a photo of the Hercules laser, which is a very powerful laser. I'll talk a little bit more about that later on. And I was able to go ahead and do a lot of great work there. Part of it was from being able to work with a team of people who collaborated with people from around the world. And I really liked the collaborative environment. I really liked feeling comfortable talking to lots of different people. This institution was a center, so it was a center for ultrafast optical sciences. And there was a lot of people that I could go to ask questions, bounce ideas off of, get feedback from. And it allowed me to do some really great work throughout grad school. But it was hard. I had been born and raised in California, and now I was at the University of Michigan. And Michigan is very far from California, and flights were very expensive. So I couldn't go back home a whole lot. And near the end of my program, unfortunately, I lost my mother and my grandmother, as well as my aunt, all within a 2-year period, right around when I was writing up my thesis. And so that was a very hard time for me. And you just feel very helpless and alone being that far away. Thankfully, the program I was in, the applied physics program, had a lot of great support structures. And when my mother was getting close to passing, they were able to go ahead and fund trips for me to go back and be with her during that time. So I'm very appreciative of that. But if I didn't have that kind of community, if I didn't have the conversation to talk to the program, talk to the faculty there, then I just have to sit that one out. And I wouldn't have the resources available to me to allow me to go be there for those really important moments. From then on, I did pretty well for myself. I had a lot of publications in my thesis, and there were reasonable journals like Physical Review Letters. I was able to win the honorable mention for the Proquist Distinguished Dissertation, which is across all majors. And then I was able to also win the John Dawson Thesis Prize, which is the thesis prize in my field. A couple of years later, I was awarded the American Indian Science and Engineering Society's Most Promising Scientist. And one of the reasons that I talk about this in this context of flights and falls is that imposter syndrome is a very real thing. And you want to, there's a board of faculty that came together to award me my thesis prize. And even then, I still have misgivings about how good of a scientist I am. Some of these comments from advisors and undergrads still haunt me to this day. And I still worry very much about whether or not I'm capable enough for the job that I currently have. And getting rid of those feelings and getting over those feelings can be very hard. In hindsight, it's pretty arrogant of me to think that I know better than this board of faculty that give me this thesis prize, where I'm like, no, I'm really not good enough. I know better than you on this. But it just kind of highlights that, successfully navigating this entire academic mission is not just something about being, purely academic and only solving physics problems. There's a lot of other factors that come in here too, and balancing things like wellness and mental health. They're just as important for long-term sustainability. In my postdoc, I worked with Dr. Margaret Mernon, who is a fantastic, well-known advisor who really set me up for my path to faculty by having me work with a bunch of grad students and being a de facto lead of them. So as a postdoc, I was able to be almost like a pre-faculty in the sense that I was able to work with grad students, kind of steer the direction of the research on my own, really train students up so that they can do things like write, they can do things like perform experiments, and I had a really great time doing this. And throughout here, I kind of understood that's what I wanted to do. And so in conversations with Margaret on this, I was promoted to a senior research associate, and that put me in the position where I could start applying for funding kind of at the tail end of my postdoc and while I was looking for faculty positions. And then afterwards, I came to UCI. And one of the great things of being a faculty is that there's a large degree of flexibility in how you can go ahead and build your research group. And I could take my own values and I can incorporate them into the science that I wanted to do. And I'd like to think that I've been largely successful in doing that. I've been able to have lots of really great students come through our group. Here's some photos of some of them across the years. And what, depending on your background, this may or may not look interesting, but in plasma physics in particular, we have the absolute lowest representation of women, let alone URMs or minorities or anything else like that, across any of the other physics disciplines. And physics isn't well known for its representation anyways. So the fact that I'm able to go ahead and build up a group and have people from a lot of different perspectives come in and do work and be successful is great. And a number of our students have graduated. So for instance, Tina Tran was an undergrad that worked with us, who's now working at ASML down in San Diego. Dino Farinella is great because he worked with us on a lot of pedagogical things. How do students learn? How can students be better at learning? And when he was looking for jobs, this came up very frequently as a strength. In his current position, which was in medical imaging, he didn't have any experience in medical imaging, but because of his pedagogical background, they thought that he'd be good at teaching and training students, which is something that they would have a harder time training someone who maybe did have experience in medical imaging. And Sahel Hakimi just graduated and is doing a postdoctoral fellowship at Lawrence Berkeley Labs. And I can keep going on for a lot of the other students here. I'm very proud of all of them, and I'm very happy to have had the opportunity to work with them in our lab. Also along the way, I married, and so that happened around the same time I got tenure. And I'm really happy for the life partner I do have. Georgia Sandoval works for Intel, and she's kind of my industry counterpart, where we do a lot of outreach, and I come from it from the academic side, and she comes at it from the industry side. And she's been able, the commonality with us is that we both have these issues that we care a lot about, and we're both able to leverage our strengths and step in and try to make a difference in terms of outreach and building programs and just being out there. She was on a panel last week with the first partner of California talking about Native women's equal pay, which it turns out that, spoiler alert, women get paid a lot less than men do in this country. And in fact, for Native women, the pay gap gets bigger the more education you have, which is something that's kind of bonkers and doesn't really exist in many other different kinds of demographics that you look at. And so having a partner like this, having someone that supports me and I can support her, and we can have just this really great partnership, is also just one of the things that gets me through the day. So in my time at UCI, in addition to being able to build up great research, I've also been able to do things like try to reform some of the education that we have here. Eric Mazur from Harvard likes to point out that these models of lecturing that we have really haven't changed since ancient Greek times. And considering the amount of modernization that's happened in nearly every other aspect of our lives, we really should be looking at ways to make the higher education experience better. When I became faculty and started teaching these intro physics classes, I was mortified to discover that the average GPA in intro physics was something on the order of 2.4 to 2.5. And that's just kind of what it's agreed to be. And I was terrified by that thought, that most of the students are getting grades that would make them feel really hurt by. And there's no point where we explain that, the grades you get in high school are not what you should expect getting here at all. In fact, at the University of California, Berkeley, in the program that I was in, the average GPA for the major was just a smidge above 3.0, which that context probably would have helped me a lot in terms of my own mental health and self-worth, but also just trying to go ahead and advertise myself in terms of looking for jobs and looking for graduate opportunities. In addition, we know a lot more now than we did in the past 20 years on how to go ahead with these so-called best practices and how to make things like graduate education and undergraduate education better. So some of the things that I've been very proud of, I'm going to highlight 3 of them. One is working with our fantastic graduate students. So I'm highlighting right here, Ariana Long and Katie Wimberly, Katie who's a Calbridge alum, to develop a program called PACE, Physics and Astronomy Community Excellence. They really did most of the work, and being able to work with them to develop a structured peer mentoring program so that we can actually have a combination of understanding this whole realm of grad school from the ground floor as you step into the door, and fostering community along the way to just make the experience less awful. Having peer mentoring, having structured mentoring, having mentorship training, a lot of these things can really make the environment a lot better. And we've done this for the past 2 years, and we've seen through exit surveys and other mechanisms that students seem to be much happier, and they are able to make much more informed decisions. And the hope is that after a few years of this, we'll be in a climate where everyone's had mentoring that isn't just from their faculty advisor, but from a various array of different people in their program, and that they feel okay coming to people for help, and they feel okay talking about issues with other people. And it really can just remove a lot of the barriers that have been institutionalized. Shown up in this corner is actually, this was my prior presidential fellowship postdoc, who is now a faculty at University of Canada, Alberta, Dr. Amina Hussain. That's not what I want to point out here. What I want to point out is the space that they're in. So a lot of times we have these physics spaces that are really made for lecturing, and they might not be the best space setup for doing modern pedagogies. So for instance, you can learn a lot more about physics by talking about it with your neighbor or by working about it in a small group, but we rarely have the types of spaces even to do that. So we were able to pilot this space where we can go ahead and have students in small groups. They can sit in tables. All the furniture is very movable. The space is inviting. It looks like a place you'd want to be, as opposed to something more akin to a minimum security prison. And it has nice quality of life improvements, like things to keep the audio down. So noise reducing ceiling tiles, and then microphones that can cancel out different types of noise so that you can really hear the person speaking. So little things like this to go ahead and make the environment more productive for different types of modern pedagogy. And very recently, we've come together to make an action plan in support of our Black community, where we've taken a hard look at lots of different principles on things that we can change in order to better serve the Black community and to engage in research with the Black community better. And so we have, should be public within the next week. And so you can go to our website and see some of the things we're going to do in this first upcoming year. And hopefully it lays the foundation for being able to make to reduce a lot of the institutional racism that exists in large, long-standing structures such as ours. And so I'm in a very happy point. I've been able to win things like the Alfred P. Research Fellowship and the NSF Career Award. And so I have to say those sentences out loud so I can swallow my imposter syndrome and keep moving on with the talk. But they've been great because the flexibility of awards like this allows me to do some really great research on the side, which with the very minimal time I have left, I'll talk about real quickly. So now that we know how I got from where I was in the beginning to where I am now, I'm going to go ahead and talk about the research I do, which I talked about the brightest light. That's the name of my talk. And I'm going to talk about why we'd want a bright light at all. And to motivate this a little bit, I'm going to go back to the particle accelerator, similar to the one where my undergraduate research experience started. And so particle accelerators have been a cornerstone of particle physics for a long time, since the days of Lorentz. And we've seen a continuous trend upwards in the amount of energy these machines are able to put out up until the last couple decades or so, when we've seen a plateau in the amount of energy we're getting out of these machines. And part of the reason for that is with how they work. I'll talk a little bit about that in a moment, but in order to really push this to the next levels with existing technology, we'd have to consider things like the Fermitron, where we have a particle accelerator that just circles the Earth. And so budgets aren't that great in physics at any given moment. I doubt that they'll get to the point where we'll be able to fund something like the Fermitron, so we can go ahead and think of where we can move forward with different types of technology. And one of the ways of doing this is with so-called advanced accelerators. Why would we want particle accelerators to be more accessible? Like, we have the LHC, why do we need more of them? There's a lot of applications that we just can't entertain right now because they're too expensive and big. For instance, nuclear waste. This is one that not only is a problem that people have for nuclear power generation, but it's a particularly impactful problem for things like, say, the Southwest United States, where there's a lot of uranium mines that have just been left out in the open. So for instance, the worst nuclear accident in the United States was the Church Rock incident, where tons of uranium milling waste was spilled all over the Navajo Nation. And then we proceeded to very swiftly do something about it several decades later. And one of the big issues is that it's very expensive to deal with messes like this. And you have to just wait it out, unless you have something like a particle accelerator, which can go ahead and use nuclear interactions to incite more decay to occur that wouldn't occur naturally. Some of the other things we'd like to use particle accelerators for are things like cancer treatment, as opposed to X-ray radiation, which absorbs, being the Beer-Lambert law, so exponential decrease as you go through tissue. Particles don't obey that. They deposit their energy in a very localized area. So if you're trying to deliver a radiation dose to some place like cancer, particles can give the same dose to an area without irradiating the surrounding tissue. And if you have something like a brain tumor, you probably do a lot of extra dose to the surrounding tissue of that tumor. Finally, there's a lot of things like radionuclides and positron generation, where we use them in medical imaging all the time. And they're produced from a small handful of power plants in the world. I think it's down to 4 now. It'd be really great to have an army of particle accelerators to be able to use to recreate these nuclear interactions to generate this type of medical product that we need for things like positron emission tomography, shown here. The way we accelerate particles now is basically, in the very simplest form, we make an electric field and we have a charged particle and it'll accelerate in that field. But the problem is, if we turn the field up too high, then our particle accelerator will arc and blow up the whole accelerator. And so right now we're only able to accelerate particles with accelerations of around tens to maybe 100 mega electron volts per meter. And if you want to get to giga electron volts or tera electron volts, then you need many, many meters, if not kilometers of length. So that's kind of the problem that we're dealing with these types of particle accelerators. And this is the problem that advanced accelerators would like to solve. If instead of using something like RF cavities or parallel plates, we used something like a plasma, which is already broken down, then you can apply arbitrarily high fields and get much higher acceleration lengths. So for instance, you can get hundreds of giga electron volts per meter as opposed to mega electron volts. And then if you wanted a giga electron volt electron, you'd only need something like a centimeter of acceleration length rather than a kilometer. One of the ways we make these plasmas and accelerate them is using intense ultrafast lasers. And this was the Nobel Prize in Physics in 2018. So exactly 2 years ago when the Nobel Prize was released, Gerard Moreau and Donna Strickland won it for developing chirped pulse amplification. And as we can see in terms of the intensity lasers have been able to produce, it also plateaued for a bit. And then after this invention, which won them the Nobel Prize, we've seen a big increase in the amount of intensity we've been able to deliver to the target. Now, why is that the case? Well, consider light. If I had a laser pointer, I might be able to put out a millijoule of light in about a second. And that would be a milliwatt of power, where a watt is how much energy in how much time. And so if I plotted that as a field over time, then this would be, 1 second. And this would be my 1 millijoule is the area integrated under this curve. But what if I didn't deliver 1 millijoule in 1 second? What if I delivered in half a second? Then, because the energy, if I'm still delivering a millijoule, the area under the curve is the same, I'd have something that would double in height. I'd have twice as much power. Well, then let's half it again to 1/4 of a second. And that's kind of the concept of chirp pulse amplification, is how fast can I deliver this light and make that instantaneous power rise? If I'm able to deliver this light in a femtosecond, so this is a billionth of a second, the amount of power I have is a terawatt of peak power, which is just this enormous amount of power there. If I'm then able to take this laser, which is still not a lot of energy, it's the same amount of energy as what's coming out of a laser pointer. If I focus it down to 10 microns, which is not even as good as your eye can focus, then we would be in an electric field strength of 3 teravolts per meter. An electron sitting in there, oscillating from the Lorentz force, would be moving at relativistic velocities in that laser. And so this is the secret to how we're able to go ahead and make really intense light that can drive things at really, really high electric fields. Now, some of these numbers sound so nonsensical that they don't even make sense. So I'll provide a little bit of context. For instance, the fastest vehicle we've ever made is the space shuttle. It travels at 12,500 miles per hour. In 100 femtoseconds, though, it only goes 8 angstroms. So the distance of a couple carbon atoms. So that's how fast we're delivering this energy. So it's not a lot of energy, but it's being delivered in absurdly small time scales. And that's how we make it very, very powerful. How powerful? The US power grid is around a few terawatts. And to generate that much power, we have to burn around 150 tons of coal every single second. That's the power that we're talking about in these laser pulses. And in fact, modern laser systems are operating at the petawatt level, so 1,000 times that. And again, the reason we're able to do this, have something with the same power as the US power grid, is because it's not on for very long. It's on for so short of a time, we don't need very much energy. And so some of these very high extreme lasers that we're building in the world, one of them is just finished being built. It's the Eli NP laser over in Romania. It's 10 petawatts being delivered in 25 femtoseconds. There's a new facility being built on top of the play area where I did my graduate education. They're calling this, instead of Hercules, the Zeus laser. And it's going to be the largest laser in America at 3 petawatts in 20 femtoseconds. The National Science Foundation is building this out. And what's interesting, though, is that we're around 20 femtoseconds, 30 femtoseconds, which is pretty short, but theoretically, you can make light pulses as short as 2 to 3 femtoseconds. And if we did that, suddenly we'd have 30 petawatts and 100 petawatts. The problem is, for various reasons, the laser technology can't actually do that. But if we could figure out to do that, we'd be able to make current lasers a factor of 10 times more powerful without needing more energy. One of the reasons that this is such a big laser is because it's delivering lots, and it's not delivering a millijoule of laser energy, it's delivering hundreds of joules of laser energy. One secret we have for making lasers more intense is by exploiting a nonlinear interaction called cell phase modulation. If I have some kind of material like a glass and light comes through it, these electrons will wiggle with the electric field. But if you wiggle it too hard, they can no longer oscillate like a sinusoidal wave because they're still bound. So now you have something that's wiggling really far. It's similar to where if you turn your speakers up too high. At a low volume, your speakers can oscillate and make the sound you want. But if you turn it up too high, you start hearing distortion because the speaker can't physically move that far to produce the sound you want to hear. And what is distortion but new sounds that weren't there in the original? Likewise, when we drive material nonlinearity, we're making new colors that weren't there before. With these new colors, we can then go ahead and rearrange the colors in a way to where they'll line up and constructively interfere. And that'll give us a shorter pulse duration than if we did nothing at all. And what's nice about this is we don't actually lose any energy along the way. So this type of cell phase modulation is something we're looking at scaling into these very high power lasers. We have a laser lab at UCI, and we've been able to show that we can take a laser that's around 33 femtoseconds, which has a laser spectrum of this, shown here in the middle, and it's around 800 nanometers. And by going through pieces of glass in a careful way, we're able to broaden this laser spectrum so much that now we can make pulses down to around 7 femtoseconds. We can actually go shorter, but when the lasers get this intense, we actually need larger and larger optics so that we don't burn them. And we just couldn't afford the larger optics. So we showed that we can actually take this down to about 3 or 4 femtoseconds, but 7 femtoseconds is the smallest that we can put on our optics. The important thing is that when we focus this light down, this is 33 femtoseconds, and this is our 7 femtoseconds, and they look identical. So we aren't really losing any energy, but we're making our pulses shorter. And because the power is defined as the energy over time, we've made our intensity go up because our power goes up. So we've been able to make this power go up by a factor of 4. We've started using this in relativistic experiments. So we've used this to make some relativistic electron beams. This is our electron spectrometer showing a nice beam here. And we've showed that our fuse cycles are producing the same amount as many cycles. The key, though, is that there's 4 times as much energy in the many cycle case as in this few cycle case. Now we're trying to do some initial experiments to go ahead and take this to the Zeus laser. So on the Hercules laser, we did an experiment where we were able to show that we're able to keep the good focus and make our laser spectrum a bit broader. As the Zeus laser gets built out, we'd like to take this to the next step to really boost up that laser intensity up to hopefully the 30 petawatt level. And so that's a quick way of how I'm going to get to the brightest light. We've been able to have a lot of great papers, but the things that I'd like to point out is that in the pink is all of the grad students that have been able to work with this, and in blue are all of the people at UCI in particular that have been able to work at this, the UCI students and postdocs. And then that Nobel Prize winner, Gerard Moreau, just a shout out to a couple of the publications, he kind of pioneered the idea of thinking of cell phase modulation for this, for these petawatt lasers, and we've been able to work with him on some experiments to try to make that a reality. So thank you, first and foremost, to my loving family for having the patience to let this happen, and to the organizing committee for thinking of me to go ahead and give this talk. The graduate students and undergrads who've been involved in all this research. We've had 7 grad students, 3 of them have graduated, and then 19 undergrads have come through our lab so far, and hopefully we'll have many more. And different agencies give me money for different things, but lastly, I'd like to thank all of you since I am just a smidge past 5 o'clock and I don't want to take up any more of your time than I have to. But thank you so much for this opportunity. I really appreciate it.
All right. I don't know if my video is showing up. It's not on mine. Thank you for a fantastic talk. I'd love to open the floor to questions. If anyone has a question and wants to pop it into the Q&A feature down there. So I'm actually curious. I will start because it seems like for some of your investigations, I didn't know there were like laser user facilities where you could take things to like these mega lasers. What kind of lasers and setups do you have in your own lab that like, what kind of investigations are you doing before you take your stuff to the mega Zeus laser?
So we have a laser in our lab that, so these big mega lasers deliver so much energy that it takes a while for them to cool down. Basically, everything gets too hot and you need to wait a little while for them to cool down. And conversely, there's new technology coming out where you can use diodes to go ahead and pump the laser with, which allows you to have a more efficient laser that can put energy out with a higher repetition rate. So the laser that we have has around the same average power, in the sense that the same amount of energy comes out if you're integrating over time. The difference is though, our laser is this kind of laser pointer millijoule laser. And it can fire 1,000 times a second. So it's like the machine gun. Whereas these larger facilities can do 1,000 millijoules or 10,000 millijoules or 100,000 millijoules. And they can fire, they're getting faster and faster, but they're still more or less on the order of 1 per second, or maybe even 1 per half hour, depending on the facility. And it's interesting you bring that up. There was an issue of access to these larger facilities because in places like Europe and Southeast Asia, they've invested lots in making these lasers kind of more commonplace. In the US, we kind of stopped doing that. And so in the last basically about 1.5 years ago, the Department of Energy stepped forward with this laser net, and the NSF stepped forward by funding Zeus to really not just make lasers, but make lasers and have access to faculty. And so in this way, I can be a faculty who doesn't have a giant laser, but I'm able to get access through vehicles such as this.
Thank you. We have a question from Wing. I noticed that you started in engineering at UMich and transitioned back to physics. Can you expand on the experience of oscillating from physics to engineering to physics?
Yeah, so I should be slightly careful. I was an engineering physics undergrad, so I still took a lot of the physics classes. And then in grad school, I was in applied physics. So it was a program, and it had the option to take some classes in physics or engineering. For the most part, I defaulted to the physics. My first advisor, I think, had a joint appointment in physics as well, but they were mostly engineering. I think at the time, though, it didn't really come to my mind that I was necessarily in a physics or an engineering kind of background. I liked the basic science aspect of it, and so I knew I wanted to do that more so than anything else. But I don't know if I can quite give the best sense of what it's like to go back and forth between the two. The other factor is that plasma physics itself is very, very odd in the sense that, you know, at UCI, plasma physics lives in the physics department, but you can find plasma physics in aerospace or nuclear engineering or mechanical engineering, really depending on where those faculty were at. And if you go there and work with those faculty, you know, you're in those departments, but you're still going to be learning a lot of the same plasma physics. So it's kind of this interesting mix of being an interdisciplinary field where you have a lot of core physics, but then we can't solve a lot of those problems. So we have to go to numerical solutions or simulations or other things to elucidate a lot of the more complex physics.
Thank you. All right, any other questions?
I haven't seen anything else pop up in the Q&A, and I can't add my own, evidently.
Oh, that's why I just asked mine out loud.
Yeah, so I figured I would do that. I actually had two, one of which is, well, I guess they're both personal. The first one, based on the location that you showed for the Dry Creek Band of Indians, are they being affected by the fires that are ravaging Northern California right now in Sonoma County? Like, are your ancestral lands safe, or have there been any issues regarding that?
So the rancheria we're at now is a little bit different from our ancestral land, since there's a man-made lake that flooded a lot of them. So my great-grandfather is underneath said lake. So I think that's safe from the fire. The fires, so there's been a lot of fires in Sonoma County, unfortunately, over the past few years. And they've come right up to the rancheria. And the rancheria has its own fire department who works alongside some of the other fire departments there. And they've been able to really keep it from burning everything down in the past few years. So I think because there's been so much burn in the previous years, it's been kind of okay now because there's just not so much left to burn anymore. But it's a big issue. I mean, it came right up to the border in recent years. So,
right. I'm always amazed at how the firefighters are able to keep those lines and hold those lines. Sometimes it's astounding to me. So I'm glad to hear that.
Yeah, no, it's definitely some acts of sheer will keeping all the structures intact there for sure.
Right. My second question may relate to more for our students who are here. In talking with various students, both on my own campus in Calbridge and across the state, many students want to find their permanent job here in California. And I'm always astounded to see faculty who are able to make that happen, who grew up here in California and able to find their faculty job here in California. Do you have any advice for those students, whether they're looking for a faculty job or something else, for a good path, or just generally how to find your permanent location in California?
Yeah, so I guess I have a couple things to say on this. I should start out by saying that I'm very happy to be at UCI, but I originally didn't set out looking to only go back to California. It was UCI was a number of schools that I applied to, and at the end of the day, I was very happy to end up here. Because I wasn't even sure I'd be able to move back to California again. Certainly things like housing and the environment and everything made me worried that I just have to live somewhere else for the rest of my life. And so thankfully, you know, one of the other things UCI is able to provide is faculty housing, as well as student housing, that's very competitive to the surrounding rates. So that's something we were able to take advantage of and that we're very appreciative of. In terms of this concept of California, I never ever want to leave California. And I feel like that's a very similar sentiment along many undergrads. And it was really on the advice of some people I met through research that, to try to do an experience outside of California. And that's when I first even applied to internship opportunities outside of California. And that's how I got the Harvard position, which made me very, very happy. In fact, Dr. Catherine Haller is still the director of the undergraduate research programs there. And I don't think I would have applied without being told, no, you should try it. 8 weeks, if you get to go to a place like Harvard, might be worth it. So I did that. I was amazed to discover that it was okay. Like, the humidity was weird. Californians don't like weather very much. We're also not used to natural disasters. And so there were different kinds of things getting used to being away. But the interesting thing was that it was fine, and that after a summer, it was okay. And so that experience convinced me that I could apply to grad schools outside of California and make it work. And that was, I think, important, because you can, if you don't have a strong requirement to be in California right now, then you're just adding a complication and a constraint that you may not otherwise need. And some people do have to stay around for family reasons or other. But if your family's going to be there in 5 years, then it could be a good opportunity for you to go out, experience different places in the world, and build up that breadth, so that when you do come back, you have those variety of experiences and opportunities that you may not be able to find everywhere you want in California. There are a lot of opportunities in California. It's a big state with lots of great things, but there's a lot of other opportunities across the country too. And it's good to gain the perspective and see everything that's out there.
Great, thank you. That's some great advice for our students. And I also just want to say, as an alum of UCI physics and astronomy, I just want to thank you for all the work that you've done to help support the graduate students there. If only we had crossed paths a little sooner and I got to experience it myself.
Right.
Yeah, and I think that's the fun part of being in this job, is that you could just do it, and you could just be part of it and help. And have that giving back and have that be part of your job. And of course, I'm very committed towards academia and all, but like having my partner be there too shows that you can also do these kinds of things in a variety of different career paths. And finding the right fit and finding what makes the most sense might take a couple tries. She calls it the zigzag, where you try something, and if the worst case scenario is you decide to do something else, you've actually gained a lot from that. It's hard to have that perspective early on in the undergrad experience, because you haven't had a lot of experiences yet. And it seems crazy to do something for 3 years and then just decide it's not what you want to do. But that's one of the most important things you can learn from an experience, particularly in when just doing something like a 8-week summer program. If you try a field out and realize that it's not the field for you, you've learned the most valuable thing you can learn from such an interaction.
We had one more question pop in if I want to answer, say this is the last one.
Sure, yeah.
But Javier says, have you been successful in establishing a connection or promoting more American Indians to follow careers in the sciences?
So one of the things that I've been able to do with my career award is try to develop research programs in partnership with the American Indian Science and Engineering Society, and trying to insert cultural relevance into a lot of the science programs. As much as I love UCI and I think it's a great institution, there's not necessarily anything sacrosanct about it, right? Like we have a lot of buildings of rebar and drywall, and people come there to work. And it's really the people there that really enable everything that can happen. The science that we learn isn't owned by an institution. It's not owned by a person or anything like that. But the way that it's presented often makes it look like it is. So one of the things that I'm trying to work on is how can we take things like you know, shooting lasers to make particle accelerators and make something like that a science that's owned by people. And not only that, but give it to the people. And so this little bit with a conversation on Church Rock, where, you know, there's hundreds of uranium mines all over the Navajo Nation, and there's just, it's such a large area and it's such a big problem that it's really costly to fix. It's not clear the best approach. The cleanup's going to take a long time, but in the meantime, people and livestock are getting sick and getting cancer, and, you know, people shouldn't have to deal with things like that weren't a problem 100 years ago. And yet there's science that we could be developing that might have impacts on this. And so rather than having it be give me all the money so that I can go in and do all the science and maybe it'll help someone someday, let's do a project where we can bring people in, where they can work with the community, they can gain ownership over the science, so they can go ahead and have it be part of their culture rather than the universities, and see if this is a way to go ahead and foster broader participation in the sciences down the road. The other thing that's kind of nice of being faculty is that there's a lot of other faculty out there, and, you know, we're just starting to kind of meet each other and talk. And so hopefully with, you know, we've just started doing some conversations with various other faculty. In fact, I'm advising a student now, and the CSU mentor is a Indigenous faculty at CSU Dominguez Hills. And so this started some broader conversations of, can we have a Indigenous physicist society of some kind, which you know, would be great if we can have this and start building that community and culture.
Great, thank you very much. So I just want to give a huge thanks for coming and sharing your story with us. To any students still left, if you're interested in sticking around for a chat with Franklin, let me know and I will pop a Zoom link to go to a private Zoom room in the chat. But if not, thank you very much and have a good rest of your evening.
Great, thank you everyone.
So Sarah, I'm not sure if they can actually message you in the chat.
Well, I figured they would stick around if they wanted to talk.
Yeah,
I can
Francisco's the only, yeah, you can, I mean, Francisco's the only one left, so we can let him talk.
I will just, do we want to stop recording?
Yeah, I'll stop it.
Okay. I